Good afternoon. In this presentation we're going to look at the inheritance of sex-linked genes and alleles that exhibit co-dominance. We want to compare it to the Mendelian ratios that Gregor Mendel, the Augustin monk, determined. So when he was looking at traits, he noticed that the dominant trait to the recessive trait turned up in a 3-to-1 ratio when the first generation were mixed together. So from the first filial to the second filial we saw a 3-to-1 dominant to recessive ratio. So sex linkage and co-dominance alter from this Mendelian ratio. So what we know is that the outcomes of Mendel's experiments were based on both dominant and recessive allele. There are a number of examples that demonstrate deviation from Mendel's ratios, as we've just been talking about. And the two examples we're going to look at is sex-linked inheritance and co-dominance. So let's just go back to stage 5 to year 10 a little bit when we were looking at the ultimate being topic. And we know that there are 23 pairs of chromosomes, which means there are 46 chromosomes. And this is what we call the diploid number, or 2n. Okay, so 2 times the number. 23 would be haploid number, just one lot of chromosomes, not the pairs. So of these 23 pairs of chromosome, 22 of those pairs are what we call autosomal or autosomes, and they code for generic general traits, so eye color, height, skin color, and so a lot of other traits like that. So the final pair is what we call the sex chromosomes. These are the ones that determine if you're a boy or a girl. So for females, they have 2 X chromosomes, and the males have an X and a Y. So what we know from looking at the karyotype is that they're more or less, one is a larger than the other, and the Y chromosome is much smaller. So what this tells us is not only is the Y chromosome smaller, it has less genes. If we were to have genes here and here for A and B, Y does not have the same area. There's no A or B, they're missing. So this changes the inheritance. Males receive certain traits when they're recessive based on this XY chromosome. So sex is determined by the male because the female always contributes an X chromosome. The male, as we can see in this cross here, contributes an X or a Y chromosome. So the male always determines the sex of the offspring. We're going to look at an example of sex linkage. So for sex linkage, it's physically linked to the sex chromosomes. It's physically linked to the X and Y chromosomes. So X chromosomes may also carry a few genes that code for non-sexual characteristics. So outside of the genes that will determine sex in both males and females, there are other characteristics. One of these would be blue-green color blindness. So blue-green color blindness. And males and females differ in their inheritance patterns, and that's because the Y chromosome doesn't carry as many genes as the X chromosome. Males only get 1 X chromosome, so they are XY. They only have 1 X chromosome. So they only have 1 allele with sex-linked genes. So where the Y chromosome doesn't carry these genes, so it's missing genes, they receive that gene from the X chromosome. So they will display whatever they receive from the X chromosome because the Y chromosome has missing genes. Let's look at an example of sex linkage. As we looked at before, color blindness is an example of a sex-linked gene. And there's an inability to distinguish between certain colors. So it might be the inability to distinguish between red, green, those two colors. So red and green. So the recessive allele is carried on the X chromosome. So what that is telling us that colour blindness is a recessive trait and it's carried on the X chromosome. It's not carried on the Y chromosome because again the Y chromosomes are smaller and lack alternative traits. Question says, identify the following cross of a female who carries the colourblind trait. So we can see here that because it's recessive, the capital N refers to normal vision and the little n refers to carrying the colourblind trait with a male who is not colourblind. So if they're not colourblind, they have one X that shows us they are normal vision, and the Y doesn't have a corresponding allele for that trait. So let's have a look at that cross. We can see here that the parent's gametes have been placed into the cross with the female across the top and the male down the side. So if we do the first cross, we have an X capital N, and we have an X capital N. If we look at the next one, it is an X capital N and an X little n. We then have an X capital N and the Y, and then we have an X little n and a Y. So let's look at the phenotypes. If we look at the phenotypes for the females, we have a normal vision, and they're homozygous, but we're just looking at phenotypes, so that's normal vision. And because there is one of the dominant normal vision, the females are all normal vision. Remember, phenotype is the physical appearance. So the females are not colourblind. It's not asking us whether they carry the trait, just what they appear to be. We'll now look at the males, and we see that there is one normal vision male, one colourblind. Next we'll have a look at the genotypes for this cross. So again we'll look at the females. We can see there is one homozygous, normal vision, one heterozygous. Or simply X capital N, 2, 1 X capital N, X lowercase n. Now the male genotype, we have one normal vision male, which is X capital N Y, 1 colourblind. Sorry, I should put in our ratio. Okay, so we can see that there is a different inheritance pattern depending on whether it's female or male. Because it's a recessive trait, the female would have to receive, and I'll just draw this up here, from both parents, an X little n. That is the only way the female would be colourblind. The male only ever needs to receive one of the little n's, the colourblind alleles, to be colourblind, because the other gene they receive is from the father, which is the Y chromosome. So they only need to receive one of them, despite it being a recessive trait. So vitamin D resistant rickets is a dominant trait that is controlled by a gene located on the X chromosome. So we're looking at this time a dominant trait. Assign genotypes for all possible outcomes for both males and females regarding the inheritance of this gene. And it says use R as the superscript for the dominant allele and lowercase r for the recessive allele. So let's look at if they have X capital R, that is an allele for rickets. We're just going to shorten it to rickets. It's vitamin D resistant rickets. Okay, and X little r is, we'll say, non-rickets. So a cross between, it says use a Punnett square to demonstrate a cross between a male with the trait and a female without rickets. And B says a cross between a female with the trait and a male without rickets. The last bit before we move on to the next slide, it says, what generalizations can we make regarding the inheritance of this trait? So let's do the crosses, and we'll come back and we'll look at that question. Okay, so for the first one, so let's have a look at this cross. We can see that if we cross the male, we can see the dominant ricket allele and the lowercase non-ricket allele, and again we can see the dominant ricket allele with the lowercase non-rickets. However, for the males, we can see that they are not receiving an allele from the female for rickets at all. So what does that tell us? So let's look at females, their genotype. We can see that all are heterozygous vitamin D resistant rickets. So we're just going to shorten that to rickets. Now we can shorten that to capital R, little r. Okay, so all of them carry that one dominant gene, so they all have rickets, but they are heterozygous for it. Okay, with the males, so they are all non-rickets. So that is X little r, Y. And the phenotype, so females, so all the offspring will be rickets. And males, all offspring non-rickets. Okay, so let's have a look at the second example here. We've got a little bit of room to have a look at the second one, and we can see a cross between a male who does not have it and a female who does have rickets, and they're carrying it on 1. So we'll do that cross, and we have a female with carrying the trait and also with rickets, a female who has non-rickets, homozygous non-rickets. We can see a male with rickets and a male without rickets. So our genotype between this cross, so let's look at female. We can see a one heterozygous rickets, two, one non-rickets. And the male, we can see one rickets, two, one non-rickets. And phenotype, females, one rickets, two, one non-rickets, And males, phenotype, we can see 1 rickets, 2, 1 non-rickets. The question before asked us what generalization can we make about the inheritance of this particular trait. So this is a dominant sex-linked trait. So what we can determine is that a male will pass it on to all of his daughters if he carries the ricket trait, and a female will pass it on to males and females, or the offspring, girls and boys, in equal proportion. So a male will pass it on to all because it's dominant, and females will pass it on to both with equal proportions. We're going to look at a summary of how X-linked genes are passed on from generation to generation. So features of an X-linked recessive trait include, so things that we can work out, is that 50% of sons of a female who carries the trait will be affected. So if a female carries the trait, 50% of sons will be affected. So all daughters of a male with the trait will be carriers of the trait. So all daughters, because the male only carries 1 X chromosome, if he has it, all the daughters will carry the trait if it's recessive. But they will not show the trait unless the mother carries the trait as well. So what's that saying in a cross is if the male has it because he's X, and we'll use a little n for saying that's the recessive trait, and Y, he passes that on to all his daughters, therefore all his daughters will carry the trait. Sons of a male with the trait will not be affected unless the mother is a carrier. So sons of a male with the trait will not be affected unless the mother is a carrier. All offspring will show the trait if both parents show the trait. In a large sample, so over many times, a large sample, more males will show the trait than females. So for colour blindness, there is more males with the colourblind trait than females. Now, if the X-linked gene is dominant, a male will pass it on to all daughters and none of his sons, because remember, he can only pass on the 1 X chromosome. So if we use a capital N this time for the males, he passes that on to all the females, all daughters that he has, they will therefore show the trait. He only ever passes on, a male will only ever pass on the Y chromosome to sons. Therefore, if he carries the trait, the dominant trait, none of his sons will have it, all of his daughters will have it. A female will pass it on to both daughters and sons. Every affected person has at least 1 person with the trait. Okay, so every affected person has at least 1 person with the trait, and over a large number of pedigrees, more females than males are affected by X-linked dominant traits. Okay, so there's slightly different outcomes, but if we break it down to the fact that males only carry 1 Y chromosome and only pass on X chromosomes to their daughters and Y chromosomes to the sons, then that starts to explain this inheritance pattern. Next thing we're going to look at is co-dominance. So this is another example that doesn't follow Mendelian patterns of inheritance. So in co-dominance, both alleles are fully expressed in a phenotype. So this is an example we're going to use for co-dominance, and it's talking about short-horned cattle. And they have both a homozygous red and a homozygous white coat. So when these pure breeding cattle are crossed, all of the offspring have what we call a rowan coat. So it's basically telling us that they have both red and white hairs. So this is an example of co-dominance. We can see it here, our homozygous red, and we're using capitals because it's dominant, and our homozygous white, and again we're using capitals because it's dominant. And when they're mixed together, we find that there is the rowan coat. So they carry 1 red allele and 1 white allele, and we see a different colour phenotype. So let's have a look at this problem. Predict the outcomes of a cross between 2 rowan coat short-horned cattle. So the parents, the P1 generation, the parents would be RW by RW. They make gametes, which would be R and W. So let's place that in here. We do our cross, we can see R and R, and we can see an R and a W. This one we can see an R, and to the side a W. This one we can see a W and a W. So our genotypes. So if we look at this, we have one homozygous red. So just for room's sake, we're just going to do the 1, 2, and we can see there are 2 Rowan coats. So 2 W, 2 1 white coat, homozygous white. So the phenotype would be 1 red, 2 Rowan, 2 1 white. So thank you for watching this presentation, Year 12, and we look forward to solving more problems in class tomorrow.